Work it, make it, do it, makes us.
Now this talk is about three different things. It's about stamped lock, number one. How many of you know what stamped lock is? Okay, so one person. That's good. You'll learn something. It might not be useful, but it might be mildly entertaining. Then we'll learn a bit about lambdas. How many of you know what lambdas are? Whoa, okay. Gee. And then something about VAR handles. How many of you know what VAR handles are? Okay, so two people know what VAR handles are. So you will learn something, which is good. Now, the first question is, why should you care what stamped lock is? Why should you know about it? Or where would you use it? Now, another question. How many of you know what a read-write lock is? Okay, that's actually pretty close to lambdas. And that's scary because that is not a very good class. You shouldn't know what that is. You should put your hands down next time if somebody asks you that. It's like saying, do you know what reflection is? Don't say yes. And the idea with stamped lock is that it gives you the read-write capability of a read-write lock, but it also, and the read-entrant read-write lock, the read lock is what we call a pessimistic read. Pessimistic means that whilst I'm reading, nobody can modify, nobody can get a write lock. That means pessimistic read lock. So a non-exclusive pessimistic read lock, that's sort of the re-entrant read-write lock. With the stamped lock, you can also do an optimistic read, which means whilst I'm reading, somebody else can actually do a write without any problems. Now, the optimistic part allows you to read fields whilst they're being modified. So if you've got a class where there are multiple fields and there's some invariant across those fields, then the stamped lock can help you to read quicker, to get better throughput, less blocking, less contention, and still be correct. You have to be a bit careful that you don't accidentally end up causing exceptions because the invariants could be temporarily broken whilst you're reading. So you must be careful of things like array index out of bounds exceptions and class casts exceptions and things, null point exceptions, things like that. Now, it's also quite a lot faster than reentrant read-write lock to use. So if you need that type of functionality, have a look at stamped lock. And there was one example, some company, I don't remember who they were, some financial guys, they wanted to have the Trove collection framework. They wanted to use that in a multi-threaded environment. Now, Trove, the idea is that it's like a collection of primitives. So if you want to have, for example, a map of int to long, for example, then with a normal hash map, you would have integer objects pointed to long objects. And you don't have great data locality, and you don't have, and you have a lot of extra objects, extra memory being used to store this. And so the idea with Trove is that you have instead just int arrays and long arrays, for example, or something like that. It's basically used a lot less memory, having primitive collections. But it's not thread safe. And so what they did was they wanted to make it thread safe, but in a way that when you're reading, you're not blocked by a writer, or the writer is not blocked by a reader, right? And they did it with stamped lock. They basically hacked into that, changed it, and used stamped lock to make it faster. Now, the stamped lock has some advantages. First of all, it's faster. Secondly, you can upgrade a read to a write lock. That sort of was the whole point of that previous puzzle before we started. So if it's not on the recording, that's too bad. Sorry. Now, it also makes you look smarter than your colleagues, because next time when somebody says, do you know what a stamped lock is, you can say, yes, I know. I've got no idea how it actually works, but I know what it is, at least, which is quite cool. Now, here's what it looks like. It's basically class since Java 8, and it gives you read and write functionality, and also optimistic read. So basically, if you say write lock on the stamped lock, you get back a number. This number will never be 0, but it might block. There are other methods like try write lock, which can return 0 if the write lock is not currently available. We've got try convert to write lock. So this would allow you to convert a read lock to a write lock, to try to convert a read lock to write lock. With the reentrant read write lock, you can never upgrade a read lock to write lock. But with this, you can try. It might not work, but then again, it might work. Okay. The next one is unlock write. So with unlock write, it checks that you really are holding a write lock rather than read lock or an optimistic read before it does the unlock. So you get an illegal monitor state exception or something like that if you get it slightly wrong. Okay. Now, the interesting thing about StampedLock, and this is not a feature, is that it's not reentrant. So if I've got a write lock and I try and get a write lock again within the same thread, it will deadlock. So that's one of the things you need to be aware of. And the other methods I've left out. You can check it out yourself. Then another, if you're doing reading, this is what we call a pessimistic read. It's a non-exclusive read. So multiple threads can read at the same time, get a read lock at the same time. Again, you're going to get the same type of method. You get a number back. Or you can have an unlock. You can try convert two read locks. So you can, for example, try convert a write lock to read lock. You can try and convert an optimistic read to read lock. And unlock read would again check that it is actually a read stamp before unlocking it. And there's also a general unlock which unlocks any stamp. Read or write, doesn't matter. Now we also have the optimistic reads, and this is not a lock, right? Because nothing is locked. It's not pessimistic, it's optimistic. And we're saying here that the optimistic read would return a 0 if the write stamp has currently been issued. So if somebody, if you call optimistic read, but somebody is currently holding a write lock, it won't block you. It will immediately come back with a 0. Now, one of the keys is that you never check whether it's 0. You always assume that it's not 0 because you're being optimistic. You're not being pessimistic. You're saying, well, I'm sure it won't be 0. And then you just carry on working. And once you finish doing your work, you then check, has in the meantime anybody acquired the write lock, or maybe the write lock was actually acquired before I started. Maybe the stamp was 0. So after you've read the fields into local variables, then you call validate, and you then get back true or false whether or not it's possible that somebody has modified the fields and therefore broken an invariant by the time you come back. So that's true or false. All right, now I live on the island of Crete, and a few years ago we had a live crocodile walking around Crete. Now you can buy almost any pet that you might want in Crete, including of course, as we discovered, crocodiles, right? Together with AK-47s, and there's a working, functioning German tank on Crete, and somewhere in the south, in the mountains in the south. So, yeah, a crocodile. And this crocodile was walking around Crete, and they discovered it, and they thought, this can't be true. This must be like an April Fool's joke. They even gave him a name called Cephas, because that's a very common Cretan name. And he died because it got too cold. It does actually get cold in Crete. Where you're in London, yeah, it's warm here too. So, but it gets cold. And now, imagine that you want to go from one place to another. So I want to go from position 0,0 to 5,5. And I want to go in the diagonal line. I don't want to go and accidentally become crocodile food. So I want to go from there to there. Right? So that's good. I don't want to ever see an intermediate state, a broken invariant, where I'm seeing a partial update of the position, right? Because then I become crocodile food, and that's not very comfortable. So that's bad. We don't want to see crocodile. We don't become fertilizer for the lake. And so, in other words, we want to move X and Y together, but there are two different fields. I've got a position with a double X and a double Y, and I've got a stamped lock inside. Now, the move is very similar to reentrant lock or reentrant read-write lock, or synchronized actually, because basically all you're doing is you're saying, I'm getting a write lock. I'm saying that no one can actually read or update this whilst I'm working with it. And we update x and y together. X plus equals delta x, and y plus equals delta y. And then finally, we unlock the write lock. Okay, so when we read it, we want to make sure that we always get the correct position. We don't want to become crocodile food. So the first thing we'll do is we'll try an optimistic read. We'll try and read x and y into local variables. If we succeed, that's fantastic. Then we're happy. If we don't succeed, then we could try a few times and see whether or not we now get successful within a reasonable amount of time. Or we can say that if we can't get it optimistically, we're going to do a pessimistic read. Now, a pessimistic read still allows other threads to read at the same time, but it won't allow another thread to write whilst I'm busy reading. So this is the little benefit here. And the algorithm looks something like this. This is sort of the general idea. I first say stamp equals sl.try optimistic read, and this might give back the value 0. If it's 0, then somebody else is busy writing or might be busy writing. They have acquired the write lock, so they might be updating it. So we're not sure that the state isn't dirty, but we assume that it's not 0, because if we check that it's 0 or not, we are delaying, we're increasing the code path from the try to the validate, and it decreases our chances of being successful. That's why we never check. We just say, okay, it's not going to be 0, we'll just continue. We then read the fields into the local variables, and you have to be slightly careful here, because when you do that, you might read dirty state, so you might actually end up with array index out of bounds exceptions. Okay. Now, you obviously know that it doesn't cost anything to cause an array index out of bounds exception, or it's very, very, very cheap to cause one of those exceptions. You know that? Who knew that? Oh, that's very few. Okay. It is very, very cheap to cause a class cast exception, an array index out of bounds exception, and a null pointer exception. It's an optimization they put in because we are such dumb programmers that we cause these things all the time, right? So you might sometimes see in your output, in your log output, a null pointer exception without a stack trace. No stack trace, just null pointer exception. Who's seen that? Okay. Maybe you'll also see class cast exception. Maybe you'll see array index out of bounds exception without a stack trace. Now, you've done that before. Right? When you do it many times in the same place, it optimizes it and it takes away the thread dump. You just get back an empty null pointer exception or array index out of bounds exception. So actually, they are almost for free. You don't pay the price of fill in stack trace or get stack trace. So it actually ends up being quite cheap. Anyway, let's go back to this. You need to be careful here that you don't end up violating getting exceptions, because you are possibly reading dirty state. But we assume not. We assume everything's going to work fine. Then after we've done that, we validate whether or not the stamp is still valid, which means, first of all, stamp is not 0. And secondly, since I acquired the stamp, no one else has asked for a write stamp. Now, it can happen, of course, that you get false positives. It can happen that when validate comes back, it comes back as false, but actually the state is correct. But we're just not sure that it's not dirty, because, of course, you don't know when it's really going to be written. So it is erring on the side of caution a bit. So in my algorithm here, I just try a single time. But you could try 3, 4, 5 times before going for the pessimistic read. And so now we do a read lock, and we update the state. This means that no one can actually get the write lock whilst we're doing this. And after this, we unlock the read again. And now we've got the field values in the local variables, and we can use those for the calculation. The way that this would look for our position is like this. We would first of all get current x and current y, read them into x and y into those. Now, they might be invalid. You might have 0,5 ending up in Sifi's drawers. We don't want that. And so we check afterwards, and if it's not valid, then we simply try again with the pessimistic read lock. All right. Before I move on, are there any questions about this algorithm? Yes, sir. Okay, the question about X and Y, do they need to be volatile? They don't need to be volatile. The try-optimistic read is already a volatile read, and the validate is another memory barrier. So you don't need to make your fields volatile. Any other questions? Right. Very good. Great question. Thank you. Now, I want to show you a slightly different approach to this, how you can also write this using sort of value holder objects. So this is sort of going to atomics, atomic field updaters, unsafe. You don't know what that is. I'm not talking about this. Stop this from the recording, okay? But anyway, I'll hide this. And then also the VAR Handles, which is the Java 9 stuff. And instead of doing the code the way we did it, we could also use atomic references. So we make a holder object. For example, because it's just two doubles, I can make a double array of size 2. Or I could make another class inside that holds X and Y, right? Final fields X and Y. So an immutable class. I can do that too. And my atomic reference would now have a pointer to the double array. And I would have inside the move method, I would do something like this. I would say double array current comma next equals a new double array. So I want to write a new double array to replace the old double array. I would then say do current equals xy.get. So I get the current value that's inside the atomic reference. And I then set the next array equal to the current 0 plus delta x and current 1 plus delta y. So the array now contains the new position I want to write to. I then try to write it. Now, to support concurrency, you need to have hardware support. Without hardware support, this doesn't work. You need it. So the hardware support we get is something called compare and swap or compare and set. And compare and set is a method which what it does is it tries to update the memory location, but what you do is you pass in the existing value. So you pass in the value current, and you say, I'm expecting it to still be equal to current, and if it is equal to current, then it does a swap and it changes it to the next one. If it's not equal to current, if somebody else has updated it in the meantime, then it will come back with false, and you'll have to try a second time. Okay, so this is the typical algorithm that you'd use for this. This is a non-blocking algorithm. It doesn't. If I have 5 threads which all move at the same time, one of them will actually have success, and the other 4 will have to try again. So there's always somebody making progress at every single time. In theory, one thread could forever retry. But in practice, it won't happen, or doesn't happen, fortunately. So this is how the atomic reference works. Atomic reference means that I've got, from my position object, I've got a pointer to another object, which is atomic reference, and from there I've got a pointer to another object, which is my double array. And another way of doing this is with something called the atomic reference field updater, which means I can store my double array inside my position directly. So there's my private volatile double array. And then I can make my atomic reference field updater. This update allows me to do a compound operation like compare and swap directly on my field. So I've got one less indirection for accessing these fields. In this case, I do want to mark it as volatile, right? Because I'm going to read the value of the double array a little bit later. I'll show you that. So the tradition is if you're using reference field updaters, then in that case you want to always make your fields volatile. It's different to StampedLock. You don't need that for StampedLock, but here you need it. Now the algorithm down here is almost exactly the same as the previous one, except the way that we call compare is a bit different. Now, how many of you have children? That's pretty good. So you'll understand this analogy. When my son was very small, a friend of mine told me, You never have to tell your children anything. What they can do and what they can't do, what they should do, what they shouldn't do. You don't have to tell them anything, because they will do exactly what you do. Very good lesson. And I always kept that in mind when I saw my son doing things which weren't right. It's like, well, you know what, when I was 18, he's actually not that bad. Think about what I did when I was 18. Is this being recorded? Okay. Scratch that too, please. Anyway, so what I was saying is, we do what our parents do. Now, our Java parents are, of course, the people who wrote the JDK, right? In a way, sort of. Imagine they're our parents, right? And in Java, up to Java 6, they were very happily using AtomicReference field updaters. For example, in concurrent linked queue, they use this AtomicReference field updater. And we complained to them and said, this thing is actually quite slow. Because every time I call compare and set, it says, I wonder if you actually have the permission to do this. And so they're always checking and checking it, and this all takes time. So they were very slow. And we said, can't you change it so that it's fast, so that you can do it very quickly? And they said, no, it's impossible, you can't do it, right? You can't make this thing fast, because otherwise you'd have safety violations and blah, blah, blah. You can't do it. So what they did in Java 7 is they started using something called Unsafe, right? Now, Unsafe, you say unsafe.get unsafe to get this unsafe class. And if you show this to a Java program, they'll go, I want to know what this is all about, I want to see how this works. And so concurrent link queue was rewritten to use Unsafe instead of the AtomicReference field updater. And before that, people didn't really pay too much attention to Unsafe. I mean, some people were using it, but most were just using field updaters or atomics directly. But now that the parents were using it, it's like, well, if the father smokes, can't the son smoke? And so it sort of perpetuated, and it became a very, very commonly used class. I'm not going to ask for show of hands as to who uses Unsafe. We're not going to talk about that, right? But here's how it would be used if it actually worked, because get unsafe is only allowed from by system classes. You find the memory location within your object, the offset inside your object of where the field is, right? And then you say unsafe.object, okay, you find that over here with object field offset. And of course, you have to make sure that that's correct, because if you get the offset wrong, you're going to update random places in memory. You can peek and poke into anywhere in memory with Unsafe. And I've done that. And well, fortunately, it only did a core dump, but it could be much worse than that, right? If you're not absolutely careful, you're going to hurt yourself. Again, I've made the volatile, the double array volatile, so it's same as before. And then what you do is you say unsafe.compare and swap object, which is the same as compare and set before, but now you specify the object that you're updating the field on, and the XY offset, and current, comma, next. So all of those get updated. Now, when you want to use Unsafe, well, the answer is you don't want to use Unsafe, right? Because if you're using Java 8, they have magically managed to make field updaters fast, after all. It was possible, right? So this reputation of Unsafe must be faster is not always true. It's like quicksort is not always quick, despite the name, and it is unsafe. You can do all sorts of bad stuff with it. So we don't want to use that. We want to rather use Java 9. Now, I write a Java newsletter, and if you are on that, you want to say hi, there's a link you can go onto to say hello and ask questions. And if you're not subscribed, you can subscribe there. Now, what I want to say is the VAR handles are a better way of doing Unsafe, right? Because with VAR handles, Java 9 stuff, you have the ability to not peek and poke into random places in memory. It wraps it for you a bit. There's an interesting article here by Doug Lee that describes how you should use it and sort of the different types of accessing of fields. Most of us know volatile and non-volatile, or plain access. but there are also two other ones. There's get opaque and set opaque, and there's get acquire and set release. So if you want to know what they are, have a look at this article. It explains it very nicely. It also, the speed is the same as unsafe, so you're going to have the same performance, but it is not unsafe, it's safe. So here, for example, I've got now a fourth version of this, the position VAR handles non-blocking. And what I do is I have to create the VAR handle for my field. I do it like this. I say method handles.lookup. So there was a class called VAR handles, but they threw that out. They've only got method handles. So basically what it does is it sees whether inside your class context, where you are currently calling it from, you've got the permission to actually find that VAR handle, to find that field. So you specify the class to look in, and the reason they've got that is to also support inner classes. So you can also do VAR handles in inner classes. Comma the name of the field, which is XY, comma the type, which is a double array. And it gives you back something called a VAR handle, which you can use to update with compare and set, and volatile reads opaque, get opaque, set opaque, etc. on a field. And here's the rest. Is basically the move function. Now this looks very similar to unsafe, except I don't have to pass in the memory offset. So I can't make that mistake anymore. And I don't have to sort of jump through hoops of trying to get hold of the unsafe field. All right, so it's sort of four variations of the same thing. Now they have got something new in Java 9 for doing a real compare and swap. You see, up to now, even though it's said over here it's a compare and swap, it is actually a compare and set. It returns a Boolean. It doesn't return the memory location that was there. But over here, we have a compare and exchange volatile. What this does is it returns the value that was there. So you set the value to the new value, but you get back whatever was there if it wasn't equal to current. And so I've written this. I think it's correct. It seems to be correct. Swap result equals XY. I'll put it into the swap result to start with. So that's my field I'm going to use for holding the swap result. And I check whether the swap result is equal to or is not equal to current. If it's not equal to current, then I'm going to try it again. So the idea is that instead of sort of reading the value, and then, instead of trying to write it and then reading the value, trying to write it, and then having to read it again, if it fails, we already have the value in hand. We don't have to do another read to get it out. And I was very excited about this. I thought this is going to be much faster than the other mechanism. And it turns out that under high contention, this actually ends up being slightly slower. So very often with concurrency, things are a bit counterintuitive. It's always with performance as well. You have lots of benchmarks out there from the past, which might have been true in the past, but which nowadays are not true anymore. Things just changed. One of my favorite ones was recently, I found out that the fastest way to generate a string from an int is not, as I thought, integer.toString, but double quotes plus I, right? And I always thought the double quotes plus I was the lazy way. That's like the guys who are too lazy to do it the proper way. They're too lazy. But because it's such a common way, they actually just optimize that one. So that ends up being faster than the diligent, hard-working way, which is much longer. So very often, and please don't change your code, it's not such a big difference, right? But it is a slight difference. You can actually measure it. It's because of the optimized string concatenation. Yeah, so the distance from origin is extremely easy with this technique. You can simply say, read the current, read the XY into a current, and then we can say hypotenuse on the current array. So very, very quick. Reading is incredibly fast. And it's even easier with the other three techniques, with the VAR handle and the unsafe and the AtomicReference field update. You simply say current equals xy, and then math hypotenuse current 0, current 1. Of course, you can't say math hypot xy 0, xy 1. So you can't inline the current, because then you might have invalid state. All sorts of very strange things can happen. You can actually have a situation where the current naught is the old value, and the current 1 is a new value, all the other way around. You can have the current naught being the new value, but current 1 being the old value. You don't have any guarantees in which order values are going to be written. So once you have concurrency going on, multiple threads writing at the same time, because you've got all these pipelined instructions, you actually don't know what's going to come out. It's very risky. Okay, now this is a conditional change idiom. I've put it into my slides, and you can get my slides from, I'm sure Devox will have it later on, but I'm not going to go into the details of this. What this does, just to give you an overview, is it allows me to upgrade a read to a WriteLock. So the thing that I showed you in the beginning before we started with the map that actually deadlocked, this one you can actually try to convert a read lock to write lock. But this particular algorithm is very complicated to understand and doesn't actually give you a much better performance. In fact, it's easier to simply get a write lock, check that you're at the right position, and then unlock the write lock. So not to bother upgrading, just keep it as a write lock always. In most cases, that's going to be faster. So it's really just of academic interests. And if you wanted to do this with VAR handles, you could do like this also quite easy to do. But I don't want to go into the details because it's really, in some cases, it's not worth it to write it with the more correct or more efficient way, because the easy way ends up actually being faster. Yes, sir. You mean for this algorithm or what?
No.
For
Why should you use the StampedLock in a way of a standard re-entrant lock? Is there
which way was it now? So I've got to find my right place again. It was here, this one. Okay. So why do you use it instead of synchronize, for example? So the reason, okay, so I'll repeat the question. The question was, why should I bother using a stamp lock when I can just use synchronize or reentrant lock? Okay, it's a really good question. How many of you know the method compute_if absent in concurrent hash map? Compute_if absent. Okay, so not that many, about 10%. Compute_if absent is a new method that's been put into hash map to allow you to compute objects if the values aren't in there. So, for example, if you've got a map with a key, comma, a list of values, then it's a very convenient method. You can just have sort of a key and then a constructor or a supplier of an array of a list of values. So it's a very convenient coding pattern. The problem is that they try to guarantee in the concurrent hash map that the supplier or the function that generates the actual value is only called once. So if you've got a concurrent hash map where you have very often the same key being accessed, or similar, a relatively small set of keys, but using compute_if absent, you end up with very high contention on the map. And you actually see blocked states, the threads being blocked, because of synchronized. So contention is something that can really hurt you in performance, because you'll end up with lots of threads being blocked. You can't utilize all of your available hardware because the threads are blocked. You've got high system time because of the context switches and just the blocked state. And as a result, we want to avoid that. We want to be able to read without being stopped by somebody else who's busy writing. And similarly, when we write, we don't want anybody who's reading optimistically to stop him from writing. So the concurrent hash map at the moment allows you to modify with several threads, not an infinite number of threads, but several number of threads at the same time. You can modify it because they write to different parts of the concurrent hash map. And when you read it, they do a volatile read, so you don't have the cost of locking when you're reading. So if you do a comparison between a fully synchronized map and a concurrent hash map, you'll find that the concurrent hash map, in most cases, is going to be much faster. And so that's the benefit of separating the reads and the writes. Okay, if it's a very short read, then you might not notice a difference. But with this, you actually will notice a difference. And if you have some threads which are writing and some which are reading, this read is going to be incredibly fast. Okay. So it's another way of doing thread safety, which will give you a better performance. But what I'm saying is that if you're doing mostly reads, even this is not the fastest. If you're doing mostly reads, this is going to be faster. The VAR handle or Unsafe or the field update is going to be faster than that. So these are two alternatives. Any other questions?
With VAR handle, can you work off heap like you can with Unsafe?
Can you work off heap with VAR handles? I don't remember. We had a discussion about that, but I actually don't remember. I'm not sure. I know it was a topic, but I don't know what the conclusion was of the topic. All right, where are we? We are here. So we've done that. So this is only for academic interest. Right. Now, one of the things with these algorithms is that sometimes they can be quite annoying or difficult to master. How many of you have wanted re-entrant lock to be auto-closable? Okay, a few. So what that means, auto-closable, it means that if you, for example, open a file, you can open it in a try block, in a try round bracket, and then it automatically gets closed at the end of the try of your try clock. So even if you have an exception, it still closes the file. And you might find if you're working with IntelliJ and you have a file, you open a file input stream and so on, that it gives you a warning or a suggestion. It says, don't you want to wrap this in a try with finally or a try with resource? And so it automatically gets closed. And unfortunately, they didn't do that for lock. They did do it for file lock, by the way. So file lock does get closed at the end of the end of the try block. But they didn't do it for the reentrant lock. And it would have been really nice, because it would have meant that we could write our code a bit easier, a bit simpler to write the code. We just say try lock.WriteLock, and at the end it automatically gets unlocked. They didn't do that. So you can do it. You can sort of code around it. You can make your own. I've got a newsletter. If you look on my website, look for try with resource and lock, you'll see it. But it's not standard. So another way to do it is to have lambdas. Lambdas are very convenient for making methods pluggable. There's one little catch with lambdas. I'll get to that in a moment. So here's the old move. I basically did all this manual work of getting a WriteLock, delta plus y plus delta y, and then I unlock it right. Now this is of course less convenient than just saying public synchronized void. Public synchronized void is easier to do than just having all of this code. But wouldn't it be nice if you look at the code at the bottom, where I would say StampedLock idioms.WriteLock, I pass on a StampedLock and then a lambda that does the update, that basically does the body of this code. And you could do something similar for reentrant locks as well, if you wanted to. And so this is what the idiom would look like. You'd basically say static method WriteLock taking a StampedLock and a runnable of the write job, and this would then get the WriteLock, call the run method, and unlock the write. So here comes the problem with lambdas. Checked exceptions. Right? And checked exceptions are something which they didn't anticipate would be such an issue. They should have, because internally they've got this thing called sneaky throw, where they take a checked exception, they basically, like a whatever, I exception, SQL exception, whatever, and they actually convert it using type erasure on generics into a runtime exception. And then they throw that, and then they convert it back to whatever it really is. So when you throw an exception whilst the program is running, there's no check whether or not you're actually allowed to throw that or not. It just throws it. And so the checked exception is only happening at compile time, where it checks whether or not you've got the permission to really throw that. I love this. Just like, I'm going to see if it's every minute or how maybe you can figure out why it goes off at what time. Anyway, so this is a problem. If you want to throw exception from here, you need to use a callable or something else. But then you have to worry about the exceptions as well. So that is a problem generally with Lambdas. And I mentioned this to the architect of Lambdas, and he admitted to me that he didn't anticipate it would be such a problem. Even though there is a class called unchecked IO exception now. They should just give us a class called unchecked exception that wraps any exception. But yeah, they didn't. So here's the distance from origin, the sort of the optimistic reading, and I'm doing a read at the top. I'm doing the read again at the bottom, and then I've got a calculation with that. So one could rewrite this with the idioms as follows. I could make a current array, and then inside my read, I would read the x and the y into the two halves of the array. Unfortunately, you can't just have local variables current x and current y, because the fields, the variables you access from inside a lambda have to be final or effectively final. So that's why I'm using an array and doing that. Now, you need to be careful if you use IntelliJ, because IntelliJ sometimes gives you bad recommendations. For example, let's say that you're accessing a field. Let's say that you're modifying a field from inside a lambda, not a field, sorry, a local variable from inside a lambda. What they'll do is they'll say to you, you're not allowed to do that. But if you want, we can automatically fix that by changing the local variable into an array of size 1. And then you can change it. Okay? So that's sort of an auto-completion feature to make it work. But it's very dangerous, because if you don't do it correctly, if, for example, you've got a stream and you make it into a parallel stream, then it's no longer thread safe, and you won't pick it up very easily. So be very careful of that auto-correct feature, where they want to change your local variable to an array, because it's not necessarily going to be thread safe. In this case, it is, because the idiom itself is protecting it. But if you were to read the current, if you were to do this from multiple threads at the same time, updating this current, it would not be thread safe. All right, and then lastly, we did the hypotenuse on the current naught and current 1. The optimistic read. So this is. Wait, I think I got this wrong here. Okay, so here's how the method would look. The actual reading would be just a runnable, reading.run, and I'm doing this possibly twice. And then the actual computation would be a supply of some type that I'm giving back. And most likely the reading.run will be inlined at runtime, because it's a very short method. All right, now the conditional change idiom, again, this is academic interest, just that you can do it. You'd have basically there are two parts here. The one is a supply of type Boolean, true or false, that we're using inside the while statement up here. And the second is the actual update. And so you could put those into two lambdas. One lambda gives back a Boolean. Other lambda is, again, a runnable that we would use. And so this is how the actual idiom would look. But I don't want to spend time on this because it's really just academic interest. Now, I'm not the only one with this idea of using lambdas to make coding idioms easier to do. They also did this inside AtomicReference. Inside AtomicReference, we of course have compare and swap and compare and set, but we also now have an accumulate and get, which takes several parameters and it basically does the update for us. So it's going to have the looping inside to do the update. Okay, so lambdas will help you to implement the concurrency idioms more easily, more correctly. And there is an example where it's used. It of course can increase object creation rate, although escape analysis is our friend. It can reduce that in some cases. And another thing is the whole thing with VAR handles, that's Java 9 stuff. I know some people are still thinking about whether they should move to Java 8, and some to Java 7, and but it's the future, and we need to go there whether we like it or not, because before you know it, it's going to be end of life for Java 8, and you'll be stuck with trying to maintain Java 8 code and trying to patch the source code yourself. So you do want to move it to Java 9 as soon as you can, as soon as it's possible. And they've now moved most of the Java 9 classes to use VAR handles instead of Unsafe. Not all because of bootstrapping. Sometimes they need a class to implement VAR handles, and so they obviously can't use VAR handles for that. But for the other ones, it works. Do you have any questions? Any more questions? We've had a bunch of questions already. Yes, sir.
It seems that a lot of those examples and patterns are like low level, and obviously you need to know your access patterns to pick the right one.
Yes.
So my question is, what are the chances that one of those patterns will be ported to, let's say, Java runtime, and it will be able to detect what is your use case, and it will be able to adapt itself? Is there any chances? Because obviously that once we commit to that code and we decide on a certain use case, the chances that someone will understand it correctly are minimal. So my question is really, should we care, or should we just stick to good old-fashioned synchronized?
Okay. Interesting thing about synchronized is that it's become popular again. It was like when Java 5 was released, it was very unpopular. Like everybody was going, we want to use re-entrant lock. And so re-entrant lock became the thing that everybody does. And the reason why is that under high contention, re-entrant lock was much better than synchronized. So performance-wise, that was a good thing to do. But then what happened is that the reason why it was so much better was because of a bug in synchronized. And they fixed that, and so in Java 6, they are pretty close. Uncontended synchronized is much better than re-entrant lock. And it's easier to use. So you should prefer synchronized if you can. If you've got the choice, use synchronized. So if you've got a system where you are always writing, synchronize is your friend. For example, concurrent hash map in Java 5 used re-entrant lock. In Java 8, they changed it to using synchronized. So there's this move back to synchronized, and one of the reasons is that synchronized is more reliable than re-entrant lock, for example. It can happen with re-entrant lock that you're trying to get a lock, but the lock's not actually given to you, even though it's available. Can happen. There are bugs in re-entrant lock. Now, they fixed a few of those from Java 7 to Java 8, but it still is risky using a re-entrant lock. Plus, you might get the idiom wrong. You might put the lock inside the try, not outside the try, and stuff like that. So you actually have quite a high possibility of getting it wrong with re-entrant lock. And even if you look in Java 9, the copy and write array list, which always used to use re-entrant lock, now also uses synchronized in copy and write array list. So there is this move back to synchronized. The time that you're going to think about using this is if in production you discover that you've got high contention on a synchronized lock. That's when you start looking and saying, can I do this differently? And the first step is not to take stamped lock. The first step is to say, can I do this thread locally? Instead of using any locking, can I use a functional approach where I'm not doing locking? That's the first approach. But sometimes you get to the stage where you can't go that way, where you need to have some shared resource that is accessed from multiple threads. And in that case, a stamped lock can help you. Answer your question? Good. I think time's up. I'm going to be around today, so if you want to come up to me and say hello, welcome to.